All right, typical circuit. We come off our panel. It's our energized conductors, goes to the energized side of the bulb, and we got a neutral coming back. That's going to be the separation is 120 volts. Typically what we end up seeing. Electricity flows in, lights up our light bulb once we get our complete circuit. So again, if this light bulb is a 120 watt light bulb and I have 120 volts of service, that means I'm going to have 1 amp of electricity being used to go ahead and work that light bulb. That 1 amp will be measured on the energized conductor, and if I put an amp meter on the neutral conductor, I will also measure 1 amp on that as well. I don't need the ground wire to make this circuit work. What we want the ground wire for is just in case that electrical, the hot or ungrounded conductor, the energized conductor, in case that comes loose and energizes something, we need another pathway to catch that and trip the breaker. And again, we need to have that bond in order to make that happen. So let's build up a multi-wire circuit here. We're going to take one of our hot breakers and slide that into place. We'll take our other one and we'll slide that into place. We'll go ahead and we'll take one of our energized conductors. We'll run it to our light bulb and bring the neutral back. And we'll bring the neutral back to our neutral bus bar. All right. 120 watts on our bulb. 1 amp going out. 1 amp coming back in. Plain and simple. Now we're going to do what we call shared neutrals here. So we're going to have another light bulb that goes on there. We're going to hook that up to our opposite breaker. All right. And I guess I also want to take a moment here and talk about that staggered bus bar that we're looking at inside of our panel. So you could see that the bar on the left is taking power off of the top breaker. The bar on the right is taking power off of the bottom breaker. And I'm talking about the main disconnect at the very top of this diagram. All right. So when I have these two breakers right next to each other, even though they're both on the right side, just because of this staggered bus bar, the bottom breaker is taking its electricity off the left side. The second from the bottom breaker, or the one where the red line goes to it, is taking its power off the right side. So they're both opposite phases. One's getting when it's positive, the other one's negative. So now we energize that on the opposite phase. We bring our neutrals back in here and everything back. Both light bulbs are going to work. And we made our connection. Between the two connections, we have 240 volts. But because I connected the neutrals on there, that's going to keep both of those at 120 coming in there. So if each one of these light bulbs is 120 watts, that means each one of these light bulbs is going to allow 1 amp of electricity to flow. 1 amp is going to go into the light bulb, each one of these. 1 amp is going to come out of the light bulb on the neutral, each one of these. When I get to that point, that little black dot on there where they meet at that point in time, now I'm no longer going to have any amperage flowing down that wire. All right, they're both going to cancel each other out, and then we're going to end up having 0 amperage from that point forward. However, if I disconnect that neutral conductor, now think about what I just did. I have electricity on alternating current going in one, flowing down the neutral of the other, connecting to the neutral of the next light bulb, because I'm not connected to my neutral bus bar any longer. Now, in theory, I ended up creating a 240 volt circuit. Those bulbs are not designed to carry that much voltage. They'll probably end up burning up real quick, and that's where our problems are going to be. So here's just another bit of math. It's basically to saying the same thing with bigger numbers. If we have a 1,000 watt load, and I always like to say, use numbers of like 120. It just makes life easier. But a 1,000 watt load, I divide by 120 volts. That's going to give me 8.3 amps. That's how they come up with it. So 8.3 on each energized conductor, 8.3 on each of the neutral conductors, 0 amps after those two neutral conductors came back together. This is actually called sharing neutrals, all right? So if I have less wattage or less amperage being used on one side than the other, now I will have amperage flowing on the ones that are shared. And this is part of the reason why in those electric stoves we end up needing to have a neutral wire coming back in there, because I'm going to have those 120 volt circuits such as light bulbs and computers and timers, things like that aren't going to be 240. So they're going to be unequal, and I need to bring the balance back. So whatever the balance is, left side 8.3, right side 4.1, the balance is 4.2. That balance is what's going to be brought back to the neutral bus bar. In order to get the full load, only one side has to be running electricity while the other side is not doing anything. Then we're going to have the full load of one side. Neutrals. Neutrals cannot be cut to make this type of splice at the receptacle on a multi-wire circuit. Okay. And yeah, they're supposed to be stripped back of the insulation and then kind of flipped over it. What we don't want to have somebody do is unscrew the wire, and then all of a sudden it ends up creating a problem. Notice the upper wire, the feed is burning up. It's starting to overheat. Continuity was stopped, and that ended up creating an open circuit on there. And once we open that up, now we're creating 240 volts circuits where they're only intended to be 120 volts, and that's when you're going to start getting things overheating. All right. Now this one, if you look back at the panel, you can see we moved that second breaker up a slot. When we did that, now both of those breakers are taking power off of the same phase. Now we said before that amperage will cancel each other out, but in this case, since they're both on the same side, they're not opposites any longer, we're going to be adding them up, and now we're going to start overloading. So if I got a 20 amp breaker and 12 gauge wire, and I'm running 12 and a half on one side, 12 and a half on the other side, since they're on the same phase, we're going to actually add the amperage at this point in time. So on that neutral, because amperage doesn't disappear, it will add up, and you're going to end up having 25 amps. If you have a neutral wire where you see heated up, chances are, and sometimes when you look at these panels, it's hard to tell what goes where, when, and how, but there's a pretty good chance one of two things is happening. Either it was a shared neutral circuit, and they got the breakers on the same phase, so they're not on different phases coming in there, or I had a loose connection. That happens when we start double tapping and triple tapping underneath that neutral bus bar, and that starts creating resistance. Anyway, my neutrals are heating up, and these connections are burning, and it actually started a fire, a small fire, but a fire nonetheless inside that panel. Another multi-wire circuit. And when we deal with multi-wire circuits, if they're in different boxes, I don't have to tie them together. All right, I could keep them separate. All right. So we got shared neutral, multi-wired circuits. The black wire coming up at the top feeds the two right outlets. The red wire feeds the two left outlets coming in there. As long as the amperage is the same or whatever it is, the neutrals are going to only carry the balance, if anything, back to the neutral bus bar. All right. I do not have to have a 240 circuit or a 240 breaker on this situation. However, if I decide to make one of those outlets a split receptacle, all right, so now what I did was I separated the top and the bottom of the outlet, and I feeding the top outlet off of the red wire, and I'm feeding the bottom one off of the black wire. They're both coming off of two different phases. I'm still bringing one neutral wire coming back in here. Because that's in the same junction box, I have to tie those two together. All right. The rationale behind this is that if I turn the breaker off to one, the entire thing needs to be dead. I don't want somebody going in there and working on this and then thinking it's dead when actually it's energized by the other breaker that comes in there. All right. So if I have a split receptacle from two different breakers and they're sharing the neutral coming back, or even if they are from two different breakers, and they're not sharing the neutral. They have their own neutrals coming back in there. They need to be tied together. So when I turn the power off to that box, everything needs to be turned off. All right, the old standby. A lot of people use these 3-prong testers. They, for the most part, they're great. All right, they're quick, they're fast. They give you a result that comes in there. And sometimes when you look at them, you could see that it's doing something a little awkward or a little bit different that comes in there. So if you see one of them is dimmer, one light is dimmer than the other light, that usually tells you that you're going to have like a bootleg ground or somebody's doing something awkward. The one thing that I have found, and I didn't test this personally, I just saw it in another video somewhere, is that if this 120 volt outlet is accidentally wired as a 240 volt outlet and it's properly grounded and you plug this in there, supposedly it's going to show normal. You're going to get 2 yellow lights and everything's going to show correct on there. If you get the more expensive testers, that's going to pick that up. I myself have never run into that, but who knows if I would have noticed it if it was, because I don't take each outlet apart to look at the inside wiring. All right. But anyway, if one light in the middle, open ground, open neutral, is the light on the right. Obviously, if we don't have any electricity come to it, we don't have the energized conductor operated. Anytime you have a red light up there, that means we're going to have some sort of reverse polarity. Whether it's a hot neutral reversed or a hot ground reversed, either way it's going to be some sort of a neutral polarity. So basic home inspection procedures. They say we are supposed to look at a representative sample. You should know that definition. A representative sample is basically one per room or one on the outside on each wall. That's the minimum that we actually have to test. All right. If it's more than that, there's nothing wrong with that. Quite frankly, we try to get every single outlet that we can. Now, I'm not going to tip over china cabinets or move furniture to get to them, but if it's out in the open or I can reach to it, I'm going to go ahead and do it. I'm not going to unplug anything in order to get to the outlet, but I'm going to hit as many as I can. So I don't want to do the minimum. I want to do as much as I can, knowing what the minimum is, and that's the least that you have to do when we come to it. Our industry standard is not invasive. The 3-light tester provides for that. Can it be fooled? Yes, it can. Can we get a safe, normal reading on the 3-light tester and have a serious problem? Should we be using a more thorough instrument? That's going to be your choice, all right? Right now, there's nothing that says we have to, all right, use anything other than what's on there. All right. So what I'm going to do here is we're going to build this air conditioning system that's present here. And it's a typical connection that we normally see. And we want to talk about, is it going to work? Is it safe? What's going to protect us? And so forth. Now, just for the illustration, obviously we don't have conduit going from one to the other. But I want you to imagine that it's there. The only reason why I didn't do that is just so I can make it clear with the wires and so forth that's coming to it. All right. So I got a central air conditioning compressor cabinet outside. I have a disconnect panel that's going to it, and it's connected via conduit on there as well. Typically, that's going to end up being seal tight. I do have one red wire, one black wire, so we have phase A and phase B is connected to it. All right. I do not have a neutral that's connected to this. So the first question I always like to ask is this thing even going to work? And the answer is going to be yes. Right now there's only 2 motors that's inside that air conditioner. One motor is for the compressor that's compressing the refrigerant, and the other one is going to be for the fan that's going to be blowing the air up going across. Both of those items are 240 volt items. So because they're both 240 volts, they will be using the same amount of amperage on both sides of the fields. If I had a neutral wire on there, I wouldn't have anything flowing down the neutral wire, so I don't even need the neutral wire coming in there. So yes, this will work. Is it okay? Not only is it okay, it's a very common setup that we end up seeing here. Next question. There's no ground. All right, so is that okay? All right, so let's say there's no ground coming in there. Our problem now comes into play is if I get an electrical energized conductor come loose, and that conductor now energizes the case. That case is going to energize the air conditioning cabinet, the conduit, everything there except where that ground is failed. So even when I'm checking air conditioning units, if it's the metal seal tight and they're using that as a ground and they didn't run a separate one in there, I make sure those are tight and secure. If it isn't, then I want to make sure that there's another ground wire that comes in there to make sure that I had that ground path going back. In this situation, I'm going to, once that energized conductor comes loose, touches the box, my entire air conditioning system, over here, is ending up energized. All right. So if everything here is energized, then I'm not able to, clear that fault. If I had a ground wire coming back through it, then that ground wire would bring electricity back to the neutral, down and back to the case, get it to my neutral bus or neutral bond on here. The bond would get it onto the neutral bus bar. That would allow my free flow electricity, and that's going to go ahead and allow everything to clear the fault and allow the breaker to trip. And that's our big audacious goal again. We want that power to turn off as fast as possible. So here we're showing if it stays energized, then whatever is going to be touching there is going to be remaining energized. We're not going to have enough flow to go ahead and trip the breakers, and that's where our problems come into play. And you still get shocked and electrocuted. So now we took a green wire, we ran a ground to our grounding bus bar. We do have our bond inside there as well. So now that wire comes loose and energizes our case, which is going to energize our ground wire. Because that bond screw is there, it's going to now energize my neutral bus bar. That neutral bus bar allows for no resistance whatsoever. So we're still going to have 5 amps go down the grounding electrode conductor, but we're going to have unlimited amps going up the neutral wire. That unlimited amps is going to be far more than the breakers, so they should be tripping instantly, and then our power's turned off and nobody's going to get hurt. That's our main goal.